That noise like haunts me in my dreams. Boop, boop. Okay, nice. They're all there. 1, 2, 3, is that right? 1, 2, 3, 4, 5, 6, 7. 7 and 9, 16. Okay. All right. I think we're all there. Last person's connecting. Grant is in. No, connecting. Olivia, everybody says they miss you today. I think we're just missing Grant now, right? Come on, Grant. Hey, Grant, you there? We can't see or hear you. You're the only one that we're waiting on. Anybody have Grant's number? Can message Grant just to tell him to rejoin if you don't mind? Thanks, guys. I appreciate that. He was joining and it was like it said it was connecting, but it was getting stuck. Hey, for those at home, what I just told those in class is I'm going to open up the floor for questions about the lab first to start. Okay, so if you want to have your lab out or what you've done so far to collect your data with any questions, knowing that the format of the lab I already emailed you. Okay, so I emailed you the format I want you to use for this lab and how you're going to go about your lab report. But questions about like, you know, did you collect your data right, or specific questions you might have, I'm going to give us like 5-10 minutes to ask those questions. They're talking right now, waiting for us to start and checking on their stuff. All right, we're going to get started. I was going to wait, but Grant will join us in a second, I'm sure. So again, like I was saying, I'm going to open up the floor just for questions about the lab. So if you have a question particularly or data, a general question about the lab format, just so you know, I did email it to you over the weekend. So if you haven't seen that yet, I would recommend you do look at that. I also put that lab format on the MyOS bulletin board page. Okay, I also put a rubric for it, the way I'm going to grade the lab. So in general, I'll either give you a lab with questions in it, or you'll be writing a lab report. It's one of those two things. So this is the first time you're probably going to be writing a lab report, I'm guessing. In chemistry, I don't know if you did actual lab reports or if you did lab activities where you were more answering questions. Okay, so this is following the actual outline and setup that I gave you with the procedure, with the purpose of the lab, the data tables, graphs that you may have used. Okay. So what are some questions you might have about the lab, or what are some things that you're wondering about still or were confused about when you were doing stuff? Jaden, go ahead.
So it's what's on the internet, but then it's also the lab report. So it's that one page on the internet,
So,
website.
Yeah, good question, Jaden. So the original lab, if you remember, I gave you had like a couple questions on it. Like at the end, there were some pre-lab questions for you to think about. So those are guidelines for you for this lab, but I tried to give you a more explicit report guideline as far as what sections you should have, and that's what I sent you in the email. If you're answering for the lab for my report, I would use the guidelines I sent you as an email. You could still have those questions answered, and those can go in your conclusion, because they're probably similar questions that I would want you to be responding to anyway. But the actual activity itself with the questions, do you need to respond on there? No. I would write a one succinct lab report for this, and you could use some of those statements you're making from those questions in your lab report. Okay, but Yeah, so that was another question I was asked about with a video. You don't really need to submit a video to me. So you guys were using Pivot, if you remember, so that you could measure your speed of your object and take your data. I can see all that happening if you show it in your lab report. So in your lab report, what you really should be doing is doing things like, this is how I calculated the speed. And then you have maybe one example of calculating speed. And then after that, you have all your data. I don't need to see you calculate speed how many times? 13 times? Or no, 10 times, I guess, because it was 5 trials from the right, 5 trials from the left. I don't need to see that calculation over and over and over again. So if you did it one way for one trial, and then you ended up averaging them, show me the calculation once, talk about the fact that you averaged them, and then present your data in a clear, concise table. I don't need to see a calculation over and over and over. Now, as far as your videos that you upload to Pivot, I'm not really, I don't care personally about like how the video looked. That was for you guys to use to help you collect the data. So once you got that data from Pivot, you don't need to use the Pivot stuff anymore. If you use the graphing tool or the data tables in Pivot, that's fine. You could just screenshot that and put that right into your lab report as your data table. So that might help you if you already did it that way. But I'm not going to be going into the Pivot Interactive and like grading your video in there. Will I maybe look at that? Sure. If I think like for some reason, you know, somebody wasn't doing it right and I'm looking at their data and nothing's right, I could possibly go to that Pivot one and see it, so you can leave it there, but I'm not going to use that as part of your actual grade. Okay? It was really for you guys to practice, because I'm telling you now that we're definitely going to use Pivot where we upload videos to analyze data, just simply because of the fact that a lot of people are going to be remote half the time, and at some point I'm sure the school might be remote in the year. So I want you to be familiar with using Pivot. That's why last class I had you start by looking and learning how to upload a video and then analyzing your own video. Okay? Does that make sense at home, what I answered for Jaden? Did you all hear what I was saying? Yeah? Okay. What other questions about the lab? I'm sure there's got to be other questions. I would definitely recommend starting it tonight if you haven't gotten a chance to yet, though. I would definitely do so. It doesn't need to be, you know, an essay when you're writing it all out. I'm going to go Rebecca, then Mary. Go ahead, Rebecca.
Yeah, so for the graph on Pivot, I wasn't too sure which, like what to label on my x-axis and what to label on my y-axis.
Okay, so your goal here is that if you're using the graphs to help you, which you can, your position change would be on the vertical axis and your time would be on the horizontal axis. And if you have position, like 3 or 4 of those data points for position, as time goes on, you could find, remember, the slope of that line to help you find the speed. Technically, Rebecca, you didn't need to use a graph for this lab. So if you found the speed of the object by using the ruler feature and the stopwatch, and you measured how far it traveled and how much time, which gave you the speed, that's fine. And you don't need to use graphs. So you'll notice that I put graphs as one of the sections, and it says like insert any graphs here. It does not mean that you have to have a graph. But if you did use it and you used a straight line and you found the slope, by all means, show exactly, or show at least one of those examples of a graph, but I don't need to see 10 different graphs showing me all the speeds from every trial. Okay, I want to see that you know how to do it, the procedure's there, the calculation is correct for the one, and then the others can be all summarized in a data table, not shown over and over again. Mary? Yeah, you personally. So Mary asked for materials list. Should you put all the stuff that you use to make the ramp? Yeah, so for these kinds of labs where I kind of left it up to you to decide what you wanted to use, people at home use things that were different, people in class use things that were different. So you're going to be stating what you did or what you use for materials, and then what you did in the procedure. Like, you know, you need to create a ramp, one that's higher than the other, 2 different objects of different masses. Possibly use masking tape to hold it affixed. Consider changing the angle of the 2 ramps, so one's a little bit steeper than the other. So that'll go in your procedure, but the materials is just a list of materials that you used. Cardboard, paper, whatever else it was that you personally used. That make sense? Okay. Sean? I mean, it's up to you, honestly. Everything's going to submit through Drive. We're not doing any paper at all. And the school really is pushing no paper submissions for obvious reasons, right? So everything's going to be submitted through Drive. So if you want to type it up in a Google Doc and then just save it as a PDF, I'd recommend you do everything as a PDF. Even if you do Google Doc afterward, you can save it or export it as a PDF, just because I can actually grade a PDF a lot easier. If you send me a Google Doc, then it's going to come really messy for me to grade it, and then I have to add like comments, and I grade everything in Notability. So I'll just load your PDFs into Notability and then spend the night grading all of your labs one after the other. So that's how I usually do it. I even put a rubric on the MyLS page. I didn't make a big deal about it because I was a little bit late, but in the end, I'm going to put the rubric at the end of your lab. So if you want to save me a little bit of a headache, when you export your lab, you can add that last page as the rubric. It's right there on the bulletin board. Okay, and I'll talk about that for the next lab and say going forward, you're all going to add it every time. But I wasn't very clear about that, so I'm not going to make a big deal. Mary? No, just say a stack of textbooks. Yeah. You don't have to be that specific. I'm not going to be nitpicky. It's more so that if somebody were to repeat the lab, the idea is that you've learned how to do it and you can teach it kind of. Because as soon as you can like really teach something, it shows emphasis that you know something well. How about from home? What other questions do we have from home? Okay, I would definitely take a look at that lab tonight. I'm going to give you guys a little bit of homework tonight, which is going to be some problems from the textbook. Now, both of them are really due on Wednesday, the lab and the homework. I put online to do the work problems, the problems from the textbook tonight and to finish up the lab tomorrow night. But if you didn't start the lab at all yet, I would definitely start it tonight so that you could at least ask me questions if you have them. Okay, I would never start something the night before and then expect to get questions answered the night before. Okay, so again, if you started the lab, go on to the homework problems tonight, and you're going to see those in a little bit. Anything else from home? Okay. All right, so let's get started with what we're going to do for today. So the idea for today is that we take a little bit of time talking about those two videos that you looked at. So you looked at distance versus displacement, and then speed versus velocity. Those are the two main ideas of the videos and what they were. So let's start by asking, and I'm going to open up the floor for anybody, those at home or in class, to tell me what's the difference between displacement and distance. What's the difference between displacement and distance? What do we notice? Yeah, start with it, Kai. Go ahead. Displacement has direction as well as, is that it has direction, which distance does not have. But also, displacement is the final position minus the initial. So you can go all the way off and come back and end up 2 feet away, and your displacement's only 2. Nice, Kai. Very good. I'm trying to repeat as you say it, if that's all right. So Kai made the point to say that like displacement is a function of where you start and where you end. So you could take any path, walk around for a while, and if you end 2 feet to the right of where you started, your displacement is 2 feet. But the distance that you physically walked might be like 130 feet, but because you ended right here and you started right here, your displacement is only 2 feet. Good. And you talked about the fact that displacement has a direction also, you mentioned. So let's talk about that for a minute. What does Kai mean when he says displacement has a direction? I'm going to go home and then I might come back to you. Anybody from home? Grace, go ahead.
It means that instead of saying just like 2 meters, you say 2 meters north.
Yes, very good. So Grace, if I were to walk this direction, what might you say my displacement is? What kind of displacement do I have?
West or left.
Good. Nice, west or left. And in physics, what we're going to do is we're going to say that left or west is negative, like the x and y axis. And to the right, or what we call east, is positive. North or up is going to be positive. South or downward is going to be negative. So it's important that we use the Cartesian coordinates, right, the x, y axis, as our directional for the year. Sean. Yeah, I'm not saying north in the city. I know. Yeah, I'm not talking about real north, but I'm like on a piece of paper or on a question on a test. If it says an object travels north, we're saying that that's positive because it's up. I know it's not up in the sense of what we know as up. It's up in the plane if we're on the surface of the Earth plane. Okay, but generally speaking, you're to see on test, north is positive, south is negative, west is negative, east is positive. So displacement involves direction. I like that. Okay. Distance does not. So distance is just the magnitude, right? It's just the magnitude. What did that word mean? The word magnitude, Jaden, what did it mean to you? Yeah, it's the amount, but not the direction. So if I said, I'm traveling at a rate of 20 meters per second, I'm just giving you the magnitude, 20 meters per second, which we know is the speed of an object. But if I said I'm moving at 20 meters per second east, well, then I'm giving you magnitude and the direction is east. Therefore, I'm giving you velocity. Okay, so that's where we get into speed and velocity. Velocity, like displacement, the direction matters. And now speed, like distance, the direction doesn't matter. We see that there's a correlation there. Okay, so the two formulas that we came up with as a result of the video were really just these two. We had speed equals distance over time, and velocity equals displacement over time. Those were the real two main cruxes we came about from these videos. We said if we have a change in position, delta x, we can measure the velocity from that. If we have some distance traveled, we can measure the speed from that. Okay? So we would say that this involves a magnitude and a direction. This is just magnitude. It's a G. Okay? Magnitude and direction versus magnitude. I can't recall if this video discussed it. Did he talk about vectors? Did he use the word vector at all in the video? Okay, and I'll hold off then for now, because we're going to talk about the next section. I wanted to address it if not, though. So let's take a look at a couple examples. So what I'm looking at in the next slide are some notes, and I've put these notes on the MyLS page under 1D kinematics. Okay, these are the slides for them, and then my completed notes are there also. So all I'm going to do for today for this class is kind of jump ahead and look at a few examples. We're gonna skip the theory because you watched the two videos over the weekend, and you guys know, and you're going to find out more and more, if you don't do the video assignments and watch things, you're going to fall dramatically and drastically behind very quick. So you got to keep up with those, which is why I'm asking you to submit your notes to Drive. If I find that people aren't doing it for some reason, I might switch over to Edpuzzle, which tracks your actual motion. Now, could you hit play and walk away? Of course, anybody could do that, and it'll say you watched it. And I'll say, oh, it looks like you watched it. So then I'll be wondering what's going on at home. So just trust me, you're going to want to make sure that you're watching and keeping up with the work outside. And so what I'm saying is that I'm going to skip a lot of the theory that I would normally cover here. And again, just for the sake of time, right? Displacement, what it is, frame of reference, what that means. This first one we'll take a look at as an example real quick. This says, imagine that there's an astronaut and a shuttle that leaves from Florida and goes throughout space and ends up landing in California. And then while these astronauts are in space, a photographer gets on a plane, and he gets on a plane in Florida, and he ends up in California also. The question is, which of these two scenarios undergoes a larger displacement? Okay, and Jaden, what do you say? And Jaden said right away, he goes, it's the same. Why, Jaden? Why would it be the same? Exactly. It's from Florida to California, right? So let's say here's Florida, here's California. Here's the astronauts, right, going through space, coming back around, ending up here. Here's the photographer getting up in the air in the flight, and in the plane, coming back down. But we know that either way, the displacement is the yellow line connecting the two. Okay, so the distance traveled by the astronauts will definitely be greater. The distance traveled by the astronauts will definitely be greater. Okay, but the displacement is the same. It's the yellow line, the yellow line. So this is just to summarize displacement versus distance, okay? Questions from home? Questions here? Okay. I'm going to move on. This was just a conceptual example. And notice with a conceptual example, I didn't list numbers. I didn't list equations right now because it's conceptual. It's understanding. We're going to also look at mathematical problems in a moment. And for those, I'm going to give you a general technique that I want you to use as an approach or a method of approach. So let's skip ahead a little bit. We're going to skip example 2. This formula we already wrote down a couple slides ago, right? Velocity. What does that little bar on top of the V mean? Anyone know? That little horizontal line on top of the letter V? It could mean one of two things in math. I'm trying to wonder if you've... It could mean repeating if it's over a number. Yeah, that's a good point. Over a decimal, it means repeating. Over a variable, though. Grace, what do you think it means?
Does it mean average?
Good. It can mean average or it can mean constant. And in the case of here, we're talking about average. Okay, it means average. So this says average velocity is the displacement of an object over a given time period. You're noticing I'm putting delta t here. Most problems, though, start when time is equal to 0. So whether you call it delta t or just t, it's interchangeable. Because again, what does delta mean? It means final minus initial. So this is like the final position minus the initial. over the final time minus the initial. But almost all problems, this is 0. Okay, you like, remember when I told you guys reset the stopwatch on pivot so the problem starts at 0 time? The same concept applies. It's rare that we're going to start a problem like 10 seconds into whatever we were counting. I don't know, it wouldn't make sense to do that. Okay, so a lot of the time you're going to see this formula written without the delta symbol next to the T. Okay, without the delta symbol next to the T there. Okay. Stop me if you have a question. Okay, please, from home especially, because I'm not necessarily asking every time, so stop me if you do. So I'm going to skip this. Let's do this one quick. So here's what I want you to do. On your own, I want you to list the given information that you think is important, okay, to start. So I want you to list, I'll write this out. I want you to list the given information. I'll give you guys about 2 or 3 minutes. I then want you to list what your desired outcome is, or desired quantity. And then I want you to list the formula that you would use to get to that. Okay, try to come up with those 3 things. I'm not asking for the answer. Again, I'm not asking for the answer itself. I'm asking you to list the given information, the desired quantity, and then the formula you would use to calculate that desired quantity. So spend about 2 minutes, read through it, and then we'll come right back together. I'm asking you to list what you're looking for. I'm not saying to determine the answer right now, but list what you are looking for. So if the problem is asking you to find out, you know, what the acceleration is, you would say that A is your desired quantity. Or if it's finding time. I'm going to start listing my givens up there so you can check with my givens. Okay, I'll go slowly with it. So I listed 2 desired quantities, or sorry, 2 given quantities rather. I listed the velocity as a positive 6 meters per second. Why did I put positive? What was the indicating factor? It's going east, right? It's going east, which is what positive is, east. And then my second quantity that was given was the time period that elapsed, that entire delta t, or again, I can drop the delta and just call this t for now, 2 minutes and 17 seconds, okay? Now my formula, or my desired quantity rather, next, I'm looking for, it says, what is her go-kart's displacement? So delta x is what I'm looking for in this problem. Okay, I'm trying to find the displacement, how far her position has changed, right? Displacement is change in position. And then finally, we only have one formula so far, really. So you probably know which formula that is. And you're going to see as we go through the year, you're going to have like a formula sheet literally at some point, which I'll give you guys, but you're going to have like probably 20 to 30 formulas that you can choose from each time. So it becomes a little bit more when we have more formulas. But for now, we have only one formula. So I'll start with that one formula for now. So if I look at the formula the way it is right now, I might notice something and say, it's not written in an explicit way that gives me delta x, right? Because my desired quantity is delta x. And this does not say delta x equals. It says v bar equals delta x over delta t. So whenever I have a formula It's really important that we learn and we continue to practice solving algebraically in that formula. So if I were to solve that formula for delta x, what would that look like? How would I get delta x by itself in the formula that's given here? How would I get delta x by itself? Michaela? Very good. So Michaela said, you know what? Delta t is down here. So she's going to multiply both sides by delta t, right? And that gives us average velocity times delta t is equal to delta x. Okay, so again, she multiplied here by delta t in one instance, and over here by delta t in the other instance. Okay, what I do to one side of the equation, I must do to the other. So that's correct. So if you want to find displacement, you could take the average velocity and multiply by the time period. So we're good to go, right? We could just take 6 times 2 minutes and 17 seconds and get an answer, right? Maybe? It's funny because I have a mask on, so I'm trying to grin at you guys right now and like indicate that it's not right, but you can't see that either. So I am grinning. Why can't I just multiply 6 times 2 minutes and 17 seconds? What's the problem here? What's the disagreement going on, Mary? Say again? Not positive or negative 6, not that. Good idea though, good idea. Kai for this one? The units. What are the units of time measured in? Well, it's minutes and it's seconds. What is our standard unit we've said this year? It is seconds. Seconds is going to be the standard base unit for time. And you know what else? If I didn't know that, look at my velocity. What are the units in? Meters per second. So I need to convert my time period into all seconds first. Then 2 minutes is 120 seconds. You should kind of know that one. We don't have to use a conversion factor really. 120 seconds plus 17 seconds means it's 137 seconds. So we're going to use a time period of 137, not 2 minutes and 17 seconds. Okay, we can't multiply things whose units don't agree. So we can't have minutes in our time period if our velocity is in meters per second. Now we're going to take this formula here. Our velocity is 6 meters per second. I dropped the positive now. I was using the positive earlier to show you guys that we're going east. That's why I put that positive there as an emphasis. And our time period is 137 seconds, and that equals delta x. Well, take a look. The units work out perfectly, don't they? Oh, seconds and seconds, they cancel. What am I left with? Yeah, it's just meters. It's just meters. And why is it meters? Because we are trying to figure out the overall displacement of this object. So 6 times 137. Okay, just to save us time, I'm going to give numbers. You guys should, you have calculators, you can calculate them or should be, but I'm going to give it just to save time. Okay, 822 meters. So this is an example where we have to recognize that our units don't agree. We need to adapt and make our units agree. Now, technically speaking, I could have changed the units into minutes and figured out what 17 seconds is as a fraction of a minute, but then I would have had to change my speed from meters per second to meters per minute. I wouldn't want to make 2 changes when I can make 1. Is that clear what I'm saying? Okay, so both would work theoretically, and you would still get the same answer. But I would not want to have to change this into minutes, the 17 seconds, and then again change meters per second into meters per minute. It would just be a messy problem, or it would just be more work than it's worth. Any questions on example 3? I'm going to skip through a couple, so I might skip over others. Others that are left blank in the notes, you're welcome to practice on your own if you want a little more practice. And all the answers are there in the notes on MyLS. Okay, my completed notes are there as well. So you could always check if you want to practice some of that work as well. Like I skipped example 2, for example. And I think I might skip example 4 also. Yeah, I'm going to skip example 4 as well. Okay, we talked about velocity versus speed. I'm going to skip example 5. Okay, let's get to graphs of motion. This is what we want to focus on. So I'm ahead, I'm on slide 12 now, okay? I'm on slide 12. So the concept of the slope of a graph. This is something that we already talked about, but I want to emphasize. Some of you have picked up on it real quickly. Others are still kind of getting themselves acclimated to this idea. If I have a position versus time graph, okay, position versus time, where position is measured in meters and time is measured in seconds. If I have a scenario of a position versus time graph, what I can recognize is that if I find the slope of this graph, its units will be familiar. What would the units be of the slope? And this was part of your summer packet, if you think back. What would the units be if you had to find the slope of, say, a line that looks like that? Okay, what would the units be? And it doesn't matter what the line looks like, really. Sean, what would it be? It'd be meters per second. Where are you getting that from, Sean? Good. Remember, rise over run, right? Change in the vertical coordinates over change in the horizontal. So this would be meters divided by seconds. So we know that meters per second is what, though? What is meters per second a measurement of? Speed or velocity, either one, right? Meters per second. So what we can recognize here is that if we found slope for this graph, it would be the change in the vertical component or coordinate over the change in the horizontal, which is exactly what this is over here, right? The change in the vertical coordinate, which is x, so change means delta x, over the change in the horizontal component here, which means change in time period. So in this problem, when we look at it, we can see that whenever we find the slope of a position time graph, we get velocity. We get velocity. And that might be something you want to write down as like the overarching statement here, okay? Again, the slope of a position versus time graph is velocity. The slope of a position versus time graph is velocity. Let's take a look at a couple examples of these graphs, okay, on the next 3 slides. So I'm going to move forward to the next one. Why is this labeled as stationary object? Take a look at the graphs. We have a position time graph, and then we actually have a velocity time graph. I'll talk about the units the way they're written in a moment. Why is this considered stationary? What do you think here? What are we thinking for this problem? Anybody from home that hasn't volunteered yet? We've got about 8 of you at home that haven't volunteered yet, so anybody chime in? Why would this be a stationary object? What do you think? Olivia, what are you thinking here?
At least for the first graph, it's as time goes on, like the measurement m doesn't change. It stays the same, therefore it's not moving.
Very good. The position, or she said the measurement, the position doesn't change. That's a constant graph, isn't it? So if my position doesn't change, then I can't be moving, hence stationary. Now, from the graph and using the phrase or the concept of slope, how would you answer? If you had to answer with the word slope involved in your answer, how would you adjust it? Either Olivia or anyone else that wants to chime in, how would you use the phrase slope here to answer the question? Okay? Be careful, the way you're saying it isn't actually right. So Kai was saying the slope doesn't increase, so the position doesn't increase. You're on the right track, Kai, but it's not worded properly, what your statement was. Mary? The slope is 0. You're right, it doesn't increase, Kai, but I could have a slope of 1 and it doesn't increase and it's a slope of 1 the whole time, and I am moving then, right? So the slope is 0. The function doesn't increase. The function itself is a constant function. I can have a slope that's constant and go up the whole time for the position. So because the slope is 0, and again, the slope of a position time graph is velocity. So if the slope is 0, the velocity is 0. Again, the slope is 0, the velocity is 0. When the velocity is 0, you are not moving, you are stationary. Now, on the right graph here, let's just indicate something. Let's jot this down. This is just meters per second, right? We know second to the negative 1 means 1 over. You got to know your rules of exponents, right, from your last 2 years of math here. Anything to the negative power means it's really in the denominator. So that's just another way of writing meters per second. So notice this graph, it's hard to see because it's black. I think it's like a black line on black here. So I'm going to highlight it in red. That's what the function is right here in red. Well, the velocity is 0 the whole time. And again, we know that because as Olivia said, the position isn't changing. And as Mary said, the slope of the position function is 0. So the velocity must be 0 as well. The second one, let's take a look at uniform motion. Uniform. What does that mean? Uniform. Like you wear uniforms for sports, right? So does it mean put on some clothes and do some motion? What does it mean? What does uniform motion mean? What do you think? Sean, give me a little stab. So Sean is saying that the slope is constant the whole time, right? I go up 1 meter, it takes me 1 second. I go up another meter, it takes me another second. So the slope is the same. It's not curved. It's not increasing or decreasing. It is linear. And if I think about motion that's uniform, it's this right here. If I'm walking at a constant pace the whole time. This is uniform motion when I'm not changing my speed or not changing my velocity. Uniform motion. Another word for uniform is constant. Okay, another word for uniform is constant. So in this example, we know that the position is increasing a certain amount every time period. And therefore, what kind of a slope do we have here? What kind of a slope? Not what value, what kind of a slope do we have in this problem? What do we think? And I'm talking about the position time graph. What kind of a slope is this when a line increases? Positive. It's a positive slope, and therefore I am moving in a positive direction, in the eastward or right direction. If the graph had been drawn like this, then it would be the opposite, right? It's a negative slope, and I would be starting over here at a position of, say, 5, and I'd be walking back to the beginning. We'll call the phone. Look at the phone on the wall, guys, at home. The phone is the beginning, we'll say. So I'm depicting the blue graph. I'd be starting at some positive position and walking with a uniform negative speed until I reach 0. And it looks like that's when I'm kind of stopping-ish, right? By the way, I stopped my graph there. So the slope indicates the velocity. So negative slope means the object has a negative velocity. Positive slope means it has a positive velocity. So if we look at our example here, we know that this velocity is positive because it was a positive slope, and we see that the velocity is shown as a positive quantity. We don't know what it is. It's not listed as a number. It's fine. But this is the shape of the graph. It would be a constant velocity the whole time, and it would remain positive because, again, this slope is a constant slope the whole time. So again, the same concept, slope matters. Let's go to the third one that's a little bit tricky. So the first two are relatively straightforward, and now the third one. Okay, this is motion that involves acceleration. And we're just touching on acceleration right now. We're going to spend a lot more time on acceleration as like our next big topic. But for now, I want you to see the idea of what happens when you speed up. So this graph shows that the position doesn't change too much in the beginning, right? So I'm walking slowly. Then I get faster and faster and faster and faster and speed up. And that's where you're seeing the graph do this, right? We see the graph growing in its rate of change. Now, how do we physically see this, though? Because we can't calculate slope of a curve, right? How do you calculate the slope of a curved line? It's not possible to calculate that slope. But what you can do is you can estimate the slope at different points. So think back to last year in geometry. You learned the word tangent, and it was regarding circles. What did the word tangent mean last year in geometry with regards to circles? Who remembers the word tangent? What did it mean? Sean? At how many points? Yeah, it was a line that touched the edge, we'll say, yeah, edge of the circle at only 1 point. So here's what we can do. And you're going to learn more about this in pre-calculus, and the next year in calculus, you can do a lot with this. We could say that, you know what, if I want the velocity from the beginning to the end, I could just find like the slope between those 2 points. But I don't want the overall velocity from the beginning to end. I want to know what the velocity is at the very beginning, and then another moment later, and another moment later, etc. So instead of doing this by connecting the endpoints and finding the velocity from the beginning to end, we can instead just put a point right here and draw a nice tangent line there. See how it only touches once on the graph? Then watch what I'm going to do. I'm going to move forward in time a little bit. And I'm going to put a tangent line there. And then I'm going to go a little bit further in time. I'm going to put another tangent line here. And what do you notice about the steepness or the pitch of the tangent line? What's happening to the pitch of the tangent line as you move along this curve? It's becoming closer and closer to being vertical, yeah. So we have, in the beginning, what looks like an object with very little slope, and then more slope, and then further increasing in slope as we progress. But what did we say slope was again? Slope of a position time graph is really just velocity. So if the slope is getting bigger and bigger, the blue line, the red line, the yellow line, even steeper, it means that we must have a velocity that's increasing now. And that is shown over here on the right side. So whenever the position function curves up, we're going to see that means that the velocity is increasing. Okay, as opposed to the last example where the velocity, if you remember, was constant. The velocity in the last example was constant. This is showing where the velocity is increasing. So we're going to talk about this concept of a tangent line even more, okay, as we keep going. But that's the idea of how you would think to yourself, how do I get slope? I can't do slope because it's a curve, so we estimate it. Now, here's what I would like you to do. I want you to practice this, or mentally at least practice it. Watch what I'm doing. If I'm taking a test or I'm looking at a graph on homework or a quiz or whatever it is, I would take my pencil and just move it along the curve and only touch one spot. So watch what I'm going to do. I'm going to hold it here, and this is the beginning, right over that blue curve where it touches once right there. Then as I move the pencil along the curve, in order for it to only touch once, it has to increase in steepness. And then further, it increases in steepness. So if you try it and you move your finger or your pencil along there, you'll see that for the pencil to move along, it's got to increase its steepness. And that's what's happening with these lines here. So we did about 3 graphs there. Are there questions about the graphs? Are there questions about the graphs? I'll reiterate that the important thing right now is that you know that the slope of a position time graph is velocity. Again, the slope of a position time graph is velocity. And we can always figure that out by just looking at the units, right? As Sean said earlier, slope is the change in the vertical over the change in the horizontal. It's just meters over seconds, so it's got to be velocity, meters per second velocity. I'll emphasize it today, and I'll say it again. You'll probably hear me say it 100 times this year. The units are the most important thing in physics. The units help everything, from solving problems to checking answers to making sure everything works out right. Know your units like the back of your hand. You got to know that velocity is meters per second. And if you can't remember it, think about the English units. It's miles per hour. It's a length over a time, right? Meters is the length, seconds is the time in SI units. I'm going to probably give you guys like these. I made up flashcards last year. You could print them out at home and stuff and use them for yourself. That actually has like terms and units on the back and then examples. And I think it's a good technique to get to start using them. Yeah, Michaela. Yeah. Meters over seconds. Yep, always. Any questions at home? Okay. All right, let's move on. How are we doing on time? Can somebody give me a time check? 5 minutes? Thanks. Before the official ending time? So we'll still have technically 13 minutes after that? Is that what you mean? Okay, perfect. Perfect. Thanks, Guy. All right. Yeah, we need these times on the wall somewhere. None of the times are listed anymore. So we've got this example. Let's jump to example 8. Okay, let's jump to example 8. This example is very similar to your lab. The one difference is that we have two things meeting, but one starts after the other. In your lab, technically, you release them at the same time, right? And technically, we assumed, which is not the case, by the way, but we made this assumption, that they reached the floor at the same time, right? Think about it. Because you guys calculated the speed of your object once it was on the floor. So we're kind of assuming that when your objects were released, they reached the bottom of the ramp at the exact same moment, and then they started to come toward each other. Now, that probably didn't happen, actually. So you have to consider that when you talk about room for error, right? When you talk about reasons for error in your estimation versus your actuality. So in this problem is an example where we've got these two people, Barbara and Adam. And Barbara starts to walk toward Adam when they're 80 meters apart. Adam starts 2 seconds after Barbara, and he has a constant speed of 4.5 meters per second, while Barbara, on the other hand, has a constant speed of 2 meters per second. Notice I used the word speed. I did not say velocity. And how do we know that I can't use the word velocity right there? Good. The direction isn't given. And on top of that, if two people are walking toward each other, one of them's got to be walking negative, one's got to be walking positive, right, directionally. You can't both be walking toward each other and say both of our velocities are positive. We'd be walking side by side in this direction if we were both positive velocity. Because they're closing a gap, one must be positive, one must be negative when we talk about velocity. All right, let's keep going. It says, from the time that Barbara starts walking, how long does it take for them to meet? So we want to take the same approach. We want to look and ask ourselves, what is given? What is desired of us? What formulas may we use here? So let's start simply with given, okay? And I'm going to ask you to draw a diagram first, to draw a diagram. And Barbara is going to walk toward Adam. Let's all be consistent so we don't have a little bit of a mix-up. Let's start, ready? Let's start with Barbara on the left, just to make it safe, okay? So let's all do this together. Let's put Barbara over here. Let's put Adam over here. And let's put a gap between them. And we'll label that gap as 80 meters. And the reason I'm doing it and saying that I want you all to follow this logic is because if you switch A and B, throughout the process of the problem, all your numbers are going to be switched, your negatives are going to be switched, and then it might confuse you along the way. Now, on a real test, on homework, it does not matter, right? If I put Barbara on one side and Adam on the other, it just switches the negative sign. But I want to be consistent amongst the class, so when we learn it together now, you're all understanding it the same way. So we've got this scenario, and we're told that Barbara starts walking toward Adam, and then Adam starts 2 seconds after Barbara. And we want to know, for part A, the time, from the time Barbara starts walking, how long does it take them to meet? So I'm going to start by listing the time for Barbara is what we're looking for. Right, from the time Barbara starts walking, how long does it take for them to meet? So that's my answer for part A. We're trying to figure out the time that Barbara has been walking for. Now, here's the question. How can I express the time that Adam has been walking for in terms of Barbara's time? In terms of, right? Think about SAT. It's an SAT phrase, in terms of, meaning using the other variable. So how can I describe the time that Adam has been walking for in terms of TB, or the time Barbara has been? No, but you're on the right track. Not times here. We're not going to be timesing anything. Barbara starts 2 seconds earlier than Adam, right? So Adam starts 2 seconds after Barbara. You want to take another stab at it or no? Yeah, very good. So it's Barbara's time that she's taken to walk minus 2 seconds. Again, Adam has only been walking for the same as Barbara, but without those 2 seconds that Barbara got a head start for. Okay, so it's like Barbara's walking, she's walking for 2 seconds, and then Adam starts to walk and they meet somewhere. It's important that we recognize this relationship because it's going to allow us to solve the problem. Without this connection, we can't solve this problem. Okay, so this is given information technically. So this is desired here. Okay, and this is given down here already. Yeah, and then it looks like you did 4.5 divided by 2 to get that number. I was like, where'd you get the 2.25, you know? So we know that's given. We also know that it says, let's see, Adam starts 2 seconds after Barbara and has a constant speed of 4.5. So that's Adam. So let's write this. Now notice what I'm putting. I'm putting V. Which way is Adam going to walk, people? According to our diagram, which way will Adam walk? Let's call it out. Which way is Adam going to walk according to our diagram? Left? Left is what you said. I can't hear what you're saying. Left? Less. Left, yeah. So Adam is here, and for Adam and Barbara to meet somewhere in between, he's got to walk left. So when I write down the velocity of Adam, I'm going to write down that he moves with a negative velocity. So we're going to start with a negative sign there for Adam. And again, we're told that Adam is moving at 4.5 meters per second. And then the velocity of Barbara is given as 2 meters per second. And I'm going to leave that positive because Barbara is walking to the right. So far we've got our general setup here. We have our given information for this scenario. Now remember, our goal is to figure out the time it takes, right? Since Barbara started, the time it takes. We're looking for TB. So to do that here, we have to use some sort of an equation, right? What do we know about the displacements and the positions? What would we say here? Think about our formula. Think about our formula. The starting positions for each of these objects are different. Barbara starts at what we're going to call the beginning, right? So we can call this what, 0. And then therefore Adam is at the 80 meter mark right over here. And if we think back to our formula relates the change in position as a function of time, the change in position, okay? So if we're looking for the change in position here, we have to think about the fact that what does that really mean? Here's what it means. It means it's the final position minus the initial position. So for these problems, it matters where they start. It matters where they start. Barbara starts at 0, Adam starts at 80. Where do they end? Where do they end? That's part B, right? At what position do they meet? But with respect to one another, if they're going to meet somewhere, they must end at the same location, right? They're going to cross paths at some point. And that was your goal of the lab, to figure where those two objects met, if they crossed or actually hit. So the question I'm asking is, what can we say about x for both of these objects? Well, it's going to be the same x value for both of them. Their x0 is called the starting point, is going to be different for each of them. The x0 will be different because they're starting at different spots in the beginning, but at the end, they're ending at the same position. If they end right here, then they both ended around, I don't know, 60 meters. If they end right here, they both end around 10 meters. But they're both going to meet somewhere, and they're going to be at the same position at that moment in time. So we know that x is the same in both cases, but x0 is not, because it starts, or they start, at different positions. So watch what I'm going to do. I'm going to move the t up by multiplying by t. And now I'm going to use this, and I'm going to use this really as like a general equation right here that I'm going to solve for. And I could write this equation by moving the x0 over to one side and write it all as a function of x. So I'm just solving this by moving the t up by multiplying by t, and then moving x0 over to this side by adding it here. And I'm getting velocity times time plus my starting position equals my final position. This should be familiar. This is like seeing y equals mx plus b. It's in a standard form of a line. Again, y equals mx plus b. That's what we're physically seeing in this problem here. So when we look at this, we have to do this for both people. We've got Adam, we've got Barbara. So for Adam, let's see. For Adam, let's see. Adam started at 80 meters. So he's going to have a plus 80 there for the x0. His velocity was negative 4.5. We don't know the time, but we're going to put TA for now, for time for Adam. And we know that they end up at some position x. So what am I doing? I'm taking these values right here, plugging that in for my velocity. I'm taking this value for Adam's starting position and plugging it in right there for x0. And then I'm going to do the same thing for Barbara. Barbara's velocity is 2 times the time that Barbara's walked for, plus her starting position, which is 0. She was at the origin. And she's going to end up at that same position we're calling x. So when I look at this problem, this is why I said earlier we needed that relationship that exists right here. This relationship is so important because right now we have 3 variables. We have x, we have TA, and we have TB. 3 variables. But according to this, we only have 2 equations. So we need a third equation to help us. So let's take this expression for TA and let's plug it in using substitution method. Let's take TB minus 2 and plug that in right here. You see what I'm saying now? Substitution, this is our third equation. We've got, again, 2 equations here, but 3 variables, x, TA, and TB. We need to plug in the expression TB minus 2. Okay, TB minus 2. I'll try to use a pointer more, sorry for those at home. It's probably easier to see it this way. So I'm going to take this whole expression here, TB minus 2, and plug that in for TA. Because remember, Adam's time is 2 seconds less than Barbara's time. So this equation here, the first one for Adam becomes negative 4.5 times TB minus 2 plus 80 equal to x. And Barbara's equation is the way it was still. Barbara is still 2 TB equals x. Okay, so again, we're using this and subbing it in right there. And that's showing up right there. Okay, this subbing in here and showing up right here. And now the benefit, or the thing that's nice, is that we've got these 2 equations on the right-hand side, and we can solve them like a system of equations would. Okay, they're both equal to x, so I would use substitution method and just set the equations equal to each other, so you could solve for TB. It's like finding an intersection on a graph, if you think back to that, right? When you have a linear function, another linear function where they intersect is the solution to the system. In your algebra course from freshman year, it's the solution. Our goal is to find that solution. So let's set these equations equal. Because they're both equal to x, they must be equal to each other. And we're going to end on this. I know we're about at the end of time now. We're probably over at this point. Plus 9 plus 80 equals 2 TB. So what I did was this. I took this equation right here, or this expression on the left-hand side, and I put it over here. And I took this expression for 2 TB, and I put it over here. Because again, they both equal x. It means that these 2 expressions must equal one another. And then we can solve this for TB. Again, for the sake of time, I'll give you a number for it. It'll be 17.8. It'll be 17.8. I'm assuming, and I have to assume this, guys, for this course, I can't go through solving algebraically every equation. We're just going to waste all the time we would have to actually learn physics, okay? It's not a math class, and if you find yourself struggling to solve this, you've got to actually practice a bit more, that means. Whether it's just practicing solving equations for x when they're in 2 spots, but you've got to know how to solve this kind of an equation. So that's the time it takes for them to meet, and the final spot says, what position do they meet at? I'm going to take this answer, plug it back into my system to get the x value. So plug TV back into this equation here, and 2 times 17.8 will yield, what is that? 40, where are we? 45.6. Okay, 45.6. Now, one thing I'm going to point out, when I did this in my notes, and you're going to see the notes online, I put Adam on the left and I put Barbara on the right. So our answer here of 45.6 is 45.6, and we're talking about its position somewhere along. So it's closer to Adam, right? Closer to Adam. 45.6 is right here. 40 mark would be right down the middle. So it's closer to Adam. If you go back and you look at the way I did it, oh, sorry, 35.6, I'm sorry. Correct me, guys. Tell me to stop. That's why I got to write these numbers down ahead of time. 35.6. So this is actually closer, not to Adam, actually. Sorry, it's closer, in this case, to Barbara. The 40 mark is here, and 35.6 is over here, closer to Barbara. So if you do it the other way, where Adam's on the left and Barbara's on the right, you're going to get a number that's going to be greater than 40, indicating closer to the right-hand side and not the left-hand side for that one. So what I'd like you to practice tonight is just a couple of these problems, okay? So there's a little bit more I'm going to talk about in class. This is kind of what I talked about with the tangent line, with the slope of the tangent line for a little while, all these little tangent points I was speaking about. But I want you guys to practice these problems here, okay? So my recommendation will be to practice these problems tonight and to finish your lab tomorrow. But if you didn't start your lab tonight and practice these problems tomorrow. Okay, but either way, it's 2 nights of homework. I do not recommend that you wait until tomorrow night to do both of these assignments. Okay, on the grade book, on whatever, MyLS, I listed this assignment due tomorrow, and then I listed the lab due Wednesday. I don't honestly care which way you do it, so if you do it backwards, that's fine. So if you want to get the whole lab done tonight and submit it, that's fine, and then do this due Wednesday, that's fine also. I'm going to check them both on Wednesday, I'll tell you that right now. But I'm trying to space it out for you for your own benefit. Is that clear what I'm saying right now? Okay. Sorry, I went over at home. I know you guys probably have to go at this point. It's definitely over, right, time-wise? Oh, yeah, we're definitely way over. Okay. So those at home, if you want to hang out, if you have a question, I know you, does anyone have class after this, or you're all done, right, at this point? Isn't that how it works now in these days? So if anyone wants to hang back at home that has a question on this, feel free to hang back for a little while and ask a question. If any of you guys want to stay and ask a question, you can. If you're done, though, which you think all are, just spray down your desk and you guys can get up and start going, okay? I don't know if he's giving the dismissal anymore. Let me check. I have an email now that gives us like all these, it's like 1,000 things of instructions. I got to look. One's for seniors, one's for juniors. Let me just take a look and see what that says. Anybody going to hang back from home that has a question right now? Okay, well, have a good day, the rest of you at home, and try to get through this work over the next 2 days.